Welcome. Today we are going to be dealing with a problem that is from the 2D motion unit, and we are also going to relate it to energy. This problem says that you are moving in a car at a speed of 10 miles per hour. Outside of the car there is a bucket. Inside of the car you have a tennis ball that you're going to drop out the window in hopes of it landing in the bucket. You drop the tennis ball from a height of 0.9 meters above the top of the bucket. How far in front of the bucket should you drop the tennis ball so that it lands in the bucket? So let's draw a sketch. Here we have the street. Then on the street there's going to be a bucket. It'll just be your standard like Home Depot bucket. And up here you have a ball, and that would be like your car window where you're going to drop the ball. And the ball is 0.9 meters from the top of the bucket. So this is 0.9 meters. And what we're trying to find is the change in x, which is however far before the bucket that you need to drop the ball so that the ball will eventually end up landing inside of the bucket. Because we can't solve for the change in x directly, we're going to have to use a kinematic to find the change in time. The kinematic that we're going to choose is the change in y equals v naught t plus 1/2 ag t squared. We choose this kinematic because, first of all, we want to find the change in time, and second of all, we have the change in y, we have v naught, and we have the acceleration due to gravity, which would be negative 9.8. Once we solve using the kinematic and get that the change in time equals 0.429 seconds, we can use the velocity formula, which is velocity equals change in x over change in t, and solve for the change in x, which we then get to be 1.9 meters. The next video is our proof that these physics equations actually do work. You may be wondering, why doesn't the ball just drop right where you dropped it when you're in the car? The reason is because the ball is moving at a constant velocity when you're in the car, and once you release it from the car, it is still moving at a velocity until it slows down and goes into the bucket.
Now that Nate finished discussing how our problem relates to 2D motion, I will show you how it relates to the second topic, energy. Energy is a conserved substance like quantity with the capability to produce change. Energy does not come in different forms, however, it comes in different accounts. Working energy is the primary transfer mechanism in this topic. The problem that we chose to discuss uses working energy through a car. Now to take a look at the LOL diagram, or flow diagram. An energy flow diagram is a diagram that shows an initial position, a flow chart, and a final position. These are also known as LOL diagrams. So, in our problem, Nate is driving a car at 10 miles per hour and drops a ball from a height of 0.9 meters and needs to determine where to drop the ball in order to drop it into a bucket. So, in our first position, before the drop of the ball, we have only gravitational energy. Gravitational energy is from the Earth and the Earth only, and there is no other energy in this because the car provides the working energy, which would be in the flow diagram. The flow diagram, or our system, is Nate and the Earth, and the car is going into the system, providing working energy and allowing the system to move. The final position has kinetic and gravitational energy from the ball moving and gravity pulling it towards the Earth. Now that the diagram is complete, the equation that we would use to show this would be Eg plus W equals EK plus Eg.